I'm Cedric, Michigan State. One second.
It's very literal.
Can you hear me? Microphone's all right? Good. Okay, so intro. I have a big title, what's it called? Professor of Computational and Quantitative Genomics. But really, I'm the bloke who plays with computers and likes beef. That's kind of more or less the summary of it. So I'm just one of those matrix vendors. That's basically what I am. And that's home. So getting there again, my poor old barbecue is buried in the snow. Yeah, some of the makes you miss those trainers. Anyways, so I think we will recap a lot or repeat a lot of what Bob and the panel already said. So I feel a bit redundant here, but hopefully there's something a little bit different. And of course, I'll talk a little bit about AI. So we've all said that maybe we're not going too far with the sequence data, but maybe if we put a bit of AI as in not artificial insemination, artificial intelligence, we can have a play with it. Anyways, this one. Move, do something. No.
Hold on, screen. Yeah.
Do something. Do something. Do something. Did something. Thank you.
So Zoom thing. I had it twice.
Okay, so that's kind of, I'll skip over some of these earlier ones. I think, especially Troy already talked this very well this morning. But by and large, this seems to be where we are headed up. If we will like it or not, I don't know, but we might not have a chance. I had a conversation with somebody recently who will say that probably we'll be replacing our arrays with low-pass data, with sequence data. And they say, no, I want my array data. They say, no, we might not have a choice. It will be gone. And then I say, okay, I'll just subset my SNPs back to my 50K data and move on with life. So that might be a bit of something that might happen soon. But in the meantime, what we're doing is pretty much sequencing the key individuals, doing the imputation from lower depth to sequence level or low pass data, and then genomic selection at the sequence level. Now, this is computationally quite intense. There are ways already to do the imputation. So basically, if you go to this swim server, this is at Michigan State. It's for pigs. Just upload your 50K, you get your sequence data back from you. There are another 2 or 3 different servers out there that do this as well for other species. So, the phasing imputation, I'll skip over that. We all know the one point was phasing is important. It is the imputation itself is not so hard. The hard bit is to get those phases right. And it's not something new. We're talking about this in the context of sequence data, flow path sequence data, but basically all the providers are already doing this in one way or another. So we're either filling the blanks in the missing genotypes on the 50K, 700K, 100K, whichever it is, and especially this matching these different SNP arrays. If you go back a few years, it was a bit of a nuisance when you had your 50K version 1, version 2, version 3, the 20K, the 80K, 120K. So that's where the imputation came in. Most groups decide, okay, this is the panel we're going to use, and impute to that. Remove what you don't want, impute what is missing, and move on with life. But also can go to higher densities, and of course now for the low pass, how it moved. And that's just the pictorial side of it. I'll skip over that. Troy had much nicer pictures than this, so I'll not embarrass myself here. It is pretty big in terms of data when we move into sequence. All that Bob likes so much, I profoundly dislike. He says he doesn't care about genomic prediction. I really don't care about all this stuff. It's kind of yet another form that I have to fill out every day. So I do it because I have to, not because I enjoy it. But if you're interested in what to be done, that's really with him. I basically just listen to him. Whatever he says is good to do, I'll do it and move on with my life. But if you look at, say, a 30x file, you're going to get paired ends, so you're going to look at 2 times 30 gigs. That's your raw data. So this kind of stuff that you'll be having to store if you want to keep your raw data for posterity. Some mid-step will be the match data that's about 37 gigs in a BAM format. And when you bring it out to GBCF, it's 34 gigs. These are kind of your 2, let's say, points. One is the raw data, and the other one is the GVCF. From here, you can save yourself doing all this stuff here, and it's easier to move on to the sequence level. And this one, oops, that fingers, sorry. And this here, I normally delete this stuff. When the data is done and dusted, this is just for one single sample. So you're looking at about 1.5 gig in the VCF file. So you move just from one ugly format to another ugly format, and that's about 8 million variants. It's not so bad that it will scale up because most of these 1.5 gig is just the headers of this stuff. And my favorite compression nowadays is actually Blink, the Blink format. It's really the best way to store this kind of data. The PGM actually holds phased data, so it will come down to about 24 megs, and if you are using the older version, it's about 7.5 megs. So this really does a decent compression of the data. It's currently I think it's the best way to reduce the size of this stuff. And it is computationally intense. So we were talking a little bit about cloud. So we talk about cloud and costs, but let's say in terms of raw storage, if you're looking at 1,000 samples in 5 cubes, that's 2 TB for 1x and about 60 TB for 30x. We're talking about millions of animals, let's say 10 million animals who want all this at 1x coverage. It's a cool 20 petabytes of storage space. So it's a lot of storage, and you're looking at about 200,000-300,000 or more just to store the raw data sets. Memory, also not a great thing. Okay, now I like just the matrices. I thought, I'm done and dusted. I want 0 to a nice little matrix. That's all I really care about. But it also takes a bit of time to look at 30 million by 100,000 samples, which is not particularly a large number of animals. At 2-bit representation of 0.75 tera. Then you can bring it up to float and to double. So if you put it in a full-on double, 64 bits, you're looking at 12 terabytes to stick into RAM, and that's just your matrix of genotypes coded as 0, 1s, and 2s. Again, you don't need to code this as doubles, but you'll have to do some recasting at some point to do the calculation. So it's annoying. And if you want to put all this there, then you can just rent yourself a little bit of cloud space for $72,000 a month, which is, and you might just about get it into memory. Maybe. Okay, so it's expensive. If you go for a 3-year plan, it's $25,000, so that's a bit more affordable, I guess. So that's kind of where we are at with this. You have to do different ways, smarter ways of dealing with this data, otherwise it's just computationally expensive. When we did the phasing of the data, the imputation to sequence, that's kind of how we run it. We run it in chunks. We run this on the HPC, and we do it in batches of 50,000 genotypes. So we should go from 50K to sequence in groups of 50,000 animals each time. And we run this in 16 cores per chunk, 160 bits per chunk, 30 minutes. So it takes only 30 minutes to run each of these chunks, but we have 1,000 of these. So in total, this gives us about 16,000 cores and 160 terabytes of RAM, which we use on our HPC there. And here's the spec. So it's using about, what, half of the HPC. Takes about 21 days to run this on a single machine. If you run this on the HPC, January 1st, it takes 5 hours to run. Super cool because all the jobs on the HPC are finished or canceled and the machine is yours. On other days of the year, it will depend on when you will be able to allocate these jobs and share resources with whoever is using. But normally when you're running this, it takes about 5-6 days to get all the jobs set out and got back. But January 1st is the day to do it. And I've already lined up my next batch of 100,000 animals. Okay, real example, 34 million variants, 62,000 samples. It's bad format, again, the 500 gigs, not too bad, and the PCF is 8.5 terabytes of file file. That's kind of our phasing and imputation bit. Considerations around this, pretty much what Troy already mentioned this morning. What are we going to store and keep in these data sets? If we lose our fast queue, it will be tricky to go back to it. So this has to be kept by somewhere, by somebody. Cold storage might be the way to go. At least it's cheap, so you grab your fast queues, store them in the cheapest, put them in stacks of HDs, and leave them there until you ever need them again. That's what I've done with stuff that I haven't used anymore. your computer requirements and software, so parallelization and of I/O and processing is the way to go. These things being linear and not the way to go. But you still always end up capped by system limits. So parallelization is lovely, but it parallelizes across whatever you have. So if you have 2 cores, it's parallel to 2 cores. If you have 500 cores, it parallelizes across 500 cores. So that's kind of the compromise. There's no way around that. And of course, you can do things like smarter programming, approximations, shortcuts, dimensionality reduction, etc. So there are different ways to speed these things up. We'll get into this really, but back to what Bob was talking in terms of phasing. If he gets these phases perfectly set up, we can reduce the dimensionality tremendously in these data sets, because we do not need to keep every single genotype animal. All we need to do is to have a panel of haplotypes, which we can reference back to which bits each animal gets, and then we can reconstruct them. We did this in silico. It works. It has a 100% accuracy, but we need 100% accurate haplotypes. If we have those, each new sample of sequence is reduced to a flat file of a few kbs, because we just go and pick the bits you want. So let's say haplotype 3,500, I want to base pair 1 to 50,000, then from haplotype, so on, so you stitch it together, and all you keep is the address of the variation that you need. But you need the haplotypes for that in a good library, and they have to be correct. Okay. Now, on the industry side, you probably only have to handle the VCF files. I think the way this data is coming out is we will not be getting FASTQ files, we will be getting VCF files. That seems to be what SchemSeq is delivering now, so just the VCF. So industry might never even see the FASTQ, we just have the VCFs, which is good and bad. It's good because you don't have to deal with it. It's bad because things will change, and then there will be no way to change those VCFs back to something else. So, and of course, what are we going to get? I was going for a plus species around 70 to 120 million variants. Bob was already saying 250 million variants, so that's even more. What are we going to keep of all this? Usually within a breed, there's 10, 20 million, so there will be one set with Angus, another with the Acroches, another with the Herefords. Everybody has different sets, so how are we going to get all these things together? And after some filtering, we'll all end up with 5, 10 million SNPs. So what we keep, how do we match it? And how do we revert back? So new assemblies, the genome assembly. Well, this has to be considered, otherwise we spend a lot of money, and this data then adjusted for new things. Okay? And also, what are we going to do with all our historical data? All those millions of 50K SNPs out there, are we going to compute everything up, or are we going to just get the new sequence data and bring it back down? So these are considerations for the practical side. But the two main things is how good is this imputation anyways, and how useful is this imputed sequence. So we'll try to look at that. I don't think we've done too much of it this morning. So first bit, how is imputation? Well, actually, we did this morning, but it's basically pattern match. It's really an exercise in pattern matching. If you have the haplotypes, it's a happy place to be. You just have to match these things up and stitch them together. It's a numbers game. The more the merrier. So the bigger the reference, the better it will be. It's a relationship game as well. So the closer you are to the reference, and the reference and the target are, the better it will work. Allele frequency, and it's also a density game. If you start from 10K, you get a worse imputation than if you start from 700K, or if you start from 50K. So these are kind of your main drives for your accuracy in the imputation. And a bunch of ugly tables, which I'll try to briefly go over. But so this is single breed data. We started out with about 10,000 50K, 1,700K, and 224 individuals with sequence data. Then we had another 6,292 sequence from other breeds that are not this breed. And we have 36 in common between this real sequence and the 50K. So this is kind of this 136 is our reference animals. And we're going to have a look at a few scenarios. First is imputation. If we should be We have discussed a lot if we should be doing intermediate steps in imputation or just straight imputation, so go from 50K to 700K to sequence or straight from 50K to sequence. I'm personally convinced nowadays that we can go straight to sequence if our reference is big enough. We don't need to do it from 700K, 50K, 700K sequence. And that's largely, we used to do that really because we had a few sequence animals. Now we have much more of those, so I think we're okay to go straight from 50K to sequence. We did that in pigs, it worked well. We did it here, it also worked well. To the point, so this is your 1 step and 2 step. This is cheating because I'm self-imputing. Okay, so my 136 were part of the sequence data, so I imputed the 136 back to the sequence. So this is kind of highway robbery, but it just gives you an idea of the accuracy of imputation on these. And this funny way of representing it is just because concordance is a funny thing. While we say that low allele frequencies are not so accurate, on the other hand, they're extremely accurate as well. I have 99 blue balls and 1 red ball. What are the chances that I pick 2 balls and they're going to be blue? Very high. Okay, so it's very easy to impute stuff that is very rare. They will always be correct, although for the wrong reasons, because they're rare, you will not get right, but everything else will be just brushed over. So you will always do a reasonably good job at the most frequent one, but the magic one to look is always the middle one, these heterozygotes. So those are the ones that you want to see these numbers and see if they are doing a good job or not. But anyways, this is cheating. Just wanted to show you that you pretty much end up with reasonably similar values. We did better with 1 step here. Again, probably the 700K was not helping because I do not have the 700K in the 50K, so I kind of screwed up more than I helped my phasing, but by and large, they should be reasonably comparable. And then we can look at something a little bit more honest, where we take out those 136 samples, put them in my pocket, and then I just use them to see how well we are imputing compared with my starting 50K of those animals. So they remove these animals now. So what we have here is 6,000 animals, but not my breed of interest. Then we have 6,000 plus 88, which was left over from my breed of interest. Then just 88 from my breed of interest. And here I did a bit of round robin to increase the number of those animals. So I would do impute 35 and use everybody else and remove those and round robin so I could get these accuracies up. What we do see is when I do not have my breed of interest, my values are pretty shoddy. I have very poor prediction, very poor imputation accuracy. The heterozygotes are only at concordance, it's only at 56%. When I put those other 88, I already bring it up to 82. When I use only the 88, I'm at 85. So actually, it's not even helping for the heterozygotes because I mean certain variation that is not in the breed. But overall, I'm doing a little bit worse than using all of them. Okay, so you will great to have very large reference sets, but if you do not have something that's connected to your breed, you cannot afford. And when we come now to this imputed data, this commercial imputed data that's coming from the pipeline, we're going to see extremely different accuracies across different breeds. Some of the breeds, for example, Holstein, I have no doubt it will work fine with the Angus as well. They have large reference sets sequenced. Now, a belted Galloway, I think it's going to be a tremendously bad accuracy of the imputed sequence data, those animals. Okay? And when we bring it up to 190, we're already looking at some reasonably good imputation accuracies. And that's the average concordance. But here's the little magic number that I really want to talk about. What about we impute our 50K to sequence, and then we use the imputed sequence, the imputed 50K as our reference panel to impute our sequence. And then we look at that. And here we're doing a really good job. Okay? So, to be confirmed, but what I'm saying is that we can use our historical data, impute it up to sequence, and then include it in the reference panel to improve the imputation accuracy as we move forward. And this here gives just as well as cheating over here. Okay, so there are some interesting possibilities to explore. I want to try this a little bit more, but I think it's worthwhile having a look at that. And also pretty equations. Okay. Details of this, but by and large, that's what every man with his dog is. we're running our block models, okay? Just want to highlight the G. We'll talk a lot about the G. So that's the rest of the talk is just about this G and this GRM. Okay. Agree that GRM is a genomic relationship matrix, if you're familiar with that, and that's how we do it based on the relationships across the genotypes. So we use the genotypes to create a relationship matrix. Okay. The formula is over there, and it will look like something along these lines. Okay, so it's essentially replacing your pedigree matrix with a genomic relationship matrix. Now, one thing that we don't really talk about much is we said it's not going to add too much. Because the only way we can make any difference in our EBVs is by changing this stuff here. If we keep everything else the same, you change the G, you change your EBVs. You don't change your G, you end up with exactly the same EBVs. So what I tend to do is really look at how much the GRM is changing from one thing to the other. And that already tells me, before you even start calculating EBVs, if anything is going to happen or not. Okay. So it's only this genomic relationship matrix. For the next too many slides, I'm afraid. What we will be looking at is basically this diagonal, the upper diagonal, the upper triangle of the GRM. Okay, so I get the upper triangle, stretch it out. So we just create a vector of all these values, and then we're comparing these values. This allows you to compare GRM1 with GRM2 with GRM3 and so on, and see how different similar they are. So we just basically do a straight plot of one or the other, and then we can see how well this is working or not. So let's talk about the comparison of the GRM for imputation. These are those two scenarios we have. They have reasonable accuracies. This one is without using our breed of interest, and this one is with including our breed of interest. Okay. And here's our GRM. This is the real sequence, those 136 animals, the real sequence versus our imputed values. And we're plotting them over here. So we can see there's a little bit more variation. Some of these samples were not so well imputed, they're deviating a fair bit. Over here, it's doing a little bit better. Of course, these numbers always look fantastically great. So just looking at the correlation between GRM A and B, we always get very close to 1. We're going to explore these more visually. Okay. So if this does not change, then maybe this should not change. If we're approximating the true GRM, we should be okay with our imputation. And again, this is making no assumptions that the sequence data is correct. As Paul pointed out today, the sequence data itself might be wrong, and the GRMs that we're building with that one might not be optimal. But that's another side. Assuming this is right, we're trying to approximate this with our imputation. Also, the different there is again just a principal component of the GRM, the imputed and the real data. So we see a few of them deviating a little bit, but by and large, they're pretty much spot on where they should be. How much errors can we introduce into this stuff? Now I've got the 136 animals, and we're plotting the real values versus the noise values. So we just get our sequence data and we start adding random genotypes into it. 1% changes nothing. So 1% error. 5%. Start to spread out a little bit, but not too much. You'll see that there's no structure here because we're not doing imputation. We're just basically putting in unbiased random error, so it doesn't change too much. 10%. 20%. So 20% of the genotypes are randomly generated. Still not too bad. So there is a lot of tolerance to this. So maybe we don't need to get too fussy if our genotypes are right or not while we're doing this kind of stuff. If we're doing this just for the GRM, we probably can get away with a lot of wrong stuff. 50%. And only when you get to 100%, you really see there's absolutely no structure left in this. So even up to 50% is still approximating something. You pick up something. This, of course, will give you very bad disease, but there is a lot of tolerance that we can use. So we don't need to get too stressed about how good or bad our GRM is, and if our imputation accuracy is 0.999 or 0.97. What about panel densities? How similar is it, the real sequence with the 10K data? Now there's a fair bit of variation here. This is again subset in the sequence to 10,000 SNPs based on the market panels. Here you get a fair bit of variation. I don't like 10K data. I think it's not dense enough. When you get to 50K, it's a little bit better. Once you hit your 100K, you're already pretty much in the same place as your full sequence GRM. So changes to the GRM after 100,000 SNPs start to become rather marginal, rather minimal. So and by the way, this here I forgot to mention, this is actually 55 million SNPs. So it's a ton of SNPs. With 100,000 SNPs, you're already getting close. With 500,000, you're pretty spot on. So you can get rid of all your other, keep the change and get rid of the 55 million, and you're getting kind of the same GRM, which means the BVs are going to be identical with 500,000 or with 55 million SNPs. Only difference is you get it in 5 minutes or you get it 3 days later. 1 million and 5 million, right? So that's kind of where we are at with what we're doing now. I don't want to some old doom and gloom, and there's no point to the whole thing, but it's just good to keep a bit of a sense of how much these SNPs are actually changing anything. What about the imputed data? How did the imputed data change in relation to the original data? So 50K imputed up to sequence and now 700K imputed up to sequence. And again, we see there's not too much differences between them. So this would be your 50K in relation to the 700K, so imputed it up to 700K. And this is the 700K up to sequence. So this is a little bit fatter. The variation here is a bit tighter on this diagonal. So, and if you actually run this, what does it look like? By and large, if you're going to do a GRM with sequence data, we'll probably not go much further than we would with 100,000 SNPs or 100,000 SNPs. So business as usual is kind of going to be limited benefits. This is 50K, 700K, and sequence. The changes in prediction accuracy are very small, 1.5%, 0.6%, and we go from 0.38 to 0.39. So it's very marginal, these changes. We're improving a little bit our GRM, but not too much. So what's the point of all this? Well, makes us entertained playing with computers for months and weeks on end, but there is a point to it. This is a single breed, closely related population, and they're all quite heavily connected. You do a bit better with multi-breed populations. Here's where it starts to become more interesting. When you have disconnected populations and you want to use information from one breed to predict another breed. So think of crossbred populations, multi-breed schemes, and so on. Here, there's probably some potential interest on these. Completely different data set. Here we have 3,000 animals and 150 animals. So what we can do is use the larger population to predict these that we cannot really predict. This is not enough for prediction. The prediction accuracy will be small, but we can use some of the information from these to predict, and there the sequence does actually help a little bit. Not great, it's not solving things, but okay. There's a big one here. I always like the big one. Okay. So this is with 70K, and this is with sequence data. We see that we do, when we use the red to predict the red, we did a little bit better in this small population, so only a little bit better than it was. But especially when we're using the blue to predict the red, we increased this one here a fair bit in relation to this 0.05. So there is some opportunities to explore this connectivity, and that's where the sequence data can become useful. Again, it's going to be interesting in practice how this plays out. I don't really see Angus supplying all this information to improve the prediction accuracy of Wagyu, So there will be some commercial limitations to that. On the other hand, things like what the CDCB does might be useful, where you can start doing single predictions in groups. So have to see what are the practical dynamics on the market, but it does help a bit. Once you hit a certain threshold of information, then of course you start losing the value of that. This is really for more limited numbers of animals. Then it's worthwhile. Now, if you already have 5 million of yours, you probably put around 5 million somebody else who also be just a marginal increase. Relatedness always grows these days. Even when we are just, we do a genomic prediction with 5 million animals. If you just get the 500 per individual, you just subset it into 500 of the most related ones, you're going to get pretty much the same results if you did each of those individually, because they do kind of capture most of the information already anyhow. So you don't need to have this huge 5 million by 5 million matrix each time. You could subset it and they're pretty much in the same spot. But this is the most immediate value for sequence information. And now we can move a bit into AI. Couldn't start something like this without an AI-generated image. So this is from DALL-E. I asked it to create this futuristic-looking cow with some genotype in DNA thingy, and it came up with that. So that looks kind of nice. And the awesome bit is I actually can use it, and I don't have to worry about copyrights or any issues, etc. It's free for you, so that's kind of cool. Anyways, that's AI, or artificial intelligence, not insemination. Again, that's maybe one of the options where we can start thinking about sequence data. The genomic relationship matrix will not help much, the block will not change too much, but if we start thinking of other options, then maybe we can get somewhere. People have been trying this for a while. I've been trying for the last 10 years. I already disappoint you all. I haven't come up with a great ultimate solution to life, the universe, and everything, but we're still banging on this and trying to get there. In a perfect world, that magic world that doesn't exist, but if it did exist, we would really know the true variants, the causal variants, the stuff that's doing stuff. And then we will use only these. But we will know everything, the big effects, the big details, and also the tiny effects. And then we remove everything else, use only these for predictions. And then we will do a good job out of it. Fitting everything and just fitting the reality. So what we're talking about is, instead of using a GRM based on all the SNPs, we would use a GRM based on a subset of SNPs that are the functional ones. So we're creating a functional relationship between the individuals. Still exactly the same block, but you have to change the set each time for each trait, of course. And this, in principle, should get you closer to reality. And here's a little example of the one that we never see, the one that we...
Yes.
Yeah, of course, if I use SNPs here for prediction, I do a better job than using my full sequence in always glorious 35 million data. Both are more or less the same, but the difference is solving 35 million SNPs or solving 2 SNPs. This one here I can eyeball a verdict, or I can just do it in Excel. But again, this is, my fingers again, this is the exception rather than the rule. Most traits are polygenic. We pick up a few of the larger QTLs and everything else is hidden in the noise. So what we're doing here is treating genomic prediction as a feature selection problem. We're trying to identify the features that are relevant and get rid of the rest. Of course, that would give you the real GRM, but it's going to be quite different from the other one. Over here, what we did, we solved our SNP effects, so a SNP block. Then we ranked our SNPs based on their effects and started going backwards. So we started adding them into the model. At the top, most significant 100 SNPs, 200, 500, etc., keep on going up. Build the GRM for these and see how it relates to our full GRM. And this is our correlation between the full GRM and our subset. Initially, we don't have so many, so it's quite low. But as you get into this kind of 10,000, 20,000, start approximating. By the time you're here in the 20, 30,000 SNPs, the GRMs are identical. So anything that you're looking in this space here hardly matters. That's why we can really get away with just subsetting. I have 50 million SNPs, I can just get any random 500,000 and I'll end up in the same place. So it doesn't really matter. There's no selection going on here, no feature selection going on when you reach into this space. But over here, you can start optimizing this. And this would be the GRM of the simulated data. Remember, it's artificial intelligence, so it's artificial intelligence, methods, and artificial data as well. So we simulate the data so that we know what we're looking for here. But this is what I would like to get. And to look at 10K to 50K, basically what we always get. But now it's the true GRM, the GRM of only the QTLs versus the full GRM. And this is very different. So what we want here is a different GRM. We don't want anymore to approximate the GRM, we want to change the GRM. And here we can see that we do not have a correlation anymore between the reality and what we're getting from the relationships. End of the day, these spurious snips only add noise to the prediction. There's this soft spot over here where we start with very low prediction accuracies. And we start adding our top snips. It will hit a certain point, and then we start adding noise into the system, which degrades our prediction accuracies until it stabilizes around the GRM. You always see this kind of flat line at a certain point in time, which is basically when your GRM is 50K or 50 million is exactly the same. So it just stabilizes those accuracies. As soon as you hit this point here, you can kind of stop adding steps because it won't make any difference anymore. That's the blue one fitting the original snip effects. We can re-estimate these effects as well. So instead of just using the original effects that we estimate using 50,000 snips, we use the top 100, we estimate these effects with these. Then top 1,000, then we estimate effects so that we're trying to refit them each time. And that does improve a little bit. You can see it. Again, it goes up and it even goes further down. And then it eventually will stabilize in the same place, of course, when they approximate the same number of snips. But here are a couple of dots. The red one is my magic unknown value. That would be, I know the QTLs and I know the effects of these QTLs and want to use them. And that kind of approximates my theoretical maximum in the data, which would be this red line over here. The orange one is when I re-estimated the QTL. So let's say I magically know the QTL, but I have to estimate the effects. I don't know the actual effect sizes. I have to estimate those from the data. And we end up over here. And this blue one is when I just used, I know the QTLs somehow, and I just use the regional effects that I estimated initially from all the data. So we ended up around here. Okay, so estimating the effect does help, and we got a bit closer. Now, even if we know the truth, we will not necessarily be able to get the perfect result. First is that more snips than the actual functional variance only add noise. Okay, so if we find the truth, if we just add more stuff, it's just going to start decaying our predictions. But even the truth is not enough if there's not enough power to estimate effects. This one was reasonably easy. It's a simple genetic architecture, 100 SNPs. These SNPs are included in the data, so it's quite easy to estimate those. So there will be reasonably big effects. If you have very small effects, you need to crank up the data size a lot. And for very small effects, you will need a tremendous amount of samples to be able to estimate those effects. So even if somehow we got the QTLs, we do not necessarily have the ability to estimate those effects conditionally, unless we have enough data for that. And that will depend on the population size, relatedness, number of QTLs, and so on. And this is one of the methods that we've approached and used for this problem. This is has a nice little name there, iterative weighted G-block with local search, but also known as the kitchen sink approach to genomic prediction. It's basically throwing the whole thing and it's a strong arm approach. So at least it's reasonably, it will give you the same result always, which is okay. So given the same data, you get the same result, which is different from most of the AI methods that will give you different results each time. So what we do here is we split this any population to 3 bits. training, where we train the model, or testing, internal testing, which we use to improve the model, and that's something that we leave in a corner and we don't touch, which is to see if the model is actually doing a good job in terms of comparison. And it's quite straightforward. We do your normal weighted GBLA. So we try to optimize this diagonal, these peak values, and try to estimate the weight. So we just keep on iterating on this until the model converges. Then we are going to rank these SNPs and try to find a spot where we are doing the best. So I get the top 10%, 20%, 30%, etc. until I find more or less that curve that we had in the model where, okay, it goes up and then it goes down. So try to get that middle point where our prediction accuracies are best with a certain subset of it. Once we do that, then we go for a brute force approach of dropping out SNPs. So go through each and every one, drop it out, see if it makes the model better or worse. If the model gets better, put it back. Gets worse, put it back in. If the model gets better or stays the same, off it goes. And you iterate through all of them. So it's a local search and an exhaustive one at that. So this takes a fair bit of time depending on the number of SNPs that you're using, of course. Once we are happy with our subset, we refit the model, and then we use that for prediction, test it out. Okay, so it's quite a kitchen sink approach. But if something like this actually works, and we're getting closer to the functional side, the beauty of this is that this should hold across generations, because you're not using anymore so much the linkage structure and the relationships. You're using something that is more positive, and that should hold from one generation to the next. It should even hold across populations. You can combine multiple breeds, crosses, and then of course this can reduce the cost. So all our problems with all this big data, and okay, now how am I going to invert this really, really large matrix of genotypes? So what am I going to do with that? You can bring this down a bit. So we can go from 50 million down to 5,000, 20,000 steps that are more associated to your trait. And that makes it a bit more efficiently usable on a day-to-day basis. And that's kind of where I am at with sequence data. It's bring it up to bring it down. How well does this work? Well, again, that depends on our traits. And it really will depend on the genetic architecture of these traits. Things that are, say, nice and easy to find, you should do a very good job of picking out these effects. It separates the foreground from the background nicely. It's all happy days. If you have 10,000 of these, all small effects, all confounded within your other genotypes, it's going to be very tricky to separate them. So that's kind of where we are at. I haven't tried yet to see how far I would have to crank up the number of individuals. I just don't have genotypes for it. These are always based on real genotypes. I do not have enough real genotypes to see how many I would need to be able to separate 10,000 QTLs in a model like this. But with 10 and 100, we are up to 1,000, we are probably in a reasonable place. Time. Comparison. It's kind of what you expect is what you get. These feature selection methods do awesomely well with 10 QTL, comparison to GBLA, base A, base C, etc. Not so well when the models become more infinitesimal. So this is where across different genotypes. We see that the accuracy is always going down over time, as they should, because the population is structured, so it's harder to pick up the effect. But if there's not so many, we pick that up, we do a good job. If it's too many, we don't find the correct ones and we don't do a better job. I can use some of the goodies and notice by now already. So your good old deep learning, AI, etc. Again, we've tried a whole bunch of these in different ways, shapes and forms, multi-layer perceptrons, evolutionary neural networks, differential evolution, extreme gradient boosting, random forests, trees, and etc. We got what everybody else got. Sometimes it's good, sometimes it's bad. Changes, you know. A little bit better here, a little bit worse there, and sometimes, yay, we beat GBLA. Ooh, we lost the GBLA. Yay, we beat GBLA, and marginally better. So that's kind of what everybody has been getting with these approaches. We did one that was kind of and one that has 48. This will really work. We started with GWAS and base R, GBLUP, and then we did some differential evolution, some other more complicated evolutionary algorithms, and we got pretty close to our expected accuracies, given the heritability of the trait. And we said, yes, now we're done. And no, it didn't work on any other data. So only this one really broke the barrier of getting close to the true accuracy. All the others was again a bit better, a bit good. So what? All right, so that's the feature selection. That's where we are at. But I still am a believer. With the sequence data, we should be closer to having the functional variants in it, I hope. So there is a chance that we can find those and use those. And then we should be doing a reasonable job. But to be continued. And just 10 years now on this one, so I can probably spend another 10 banging on it. Just to wrap this one up, okay, more ChatGPT. This is probably our future on farms. It's a bit on the nosy thing. I asked him to do a farm setting in the future, DNA, and it went all jingoistic on me, but that looks cool. Anyway, so maybe this is what we will be doing on the farms in the future. We'll just be having our little robots, we do our own DNA analysis, we don't need to send stuff to labs anymore or do any of that stuff, just at the farm level. The truth is that kind of is already there in the future. Tonight, Dr. Helen Ostrowski will be giving a poster on portable sequencing, so I suggest you have a chat with her. I don't want to steal her thunder. But kind of we are here. We had all these conversations today about the complications of doing sequencing, etc. Hannah did all this in my kitchen. We had this awesome party and we did some sequencing over there. So DNA extraction, library preparation, sequencing at home. She's not a molecular biology. I won't touch it without mistake. Don't get into labs. So it's already doable. And maybe in the future, this will be the next iteration. We're talking about 10 years from now, we probably can just be doing this ourselves without any of these need for centralized labs. Okay. So really cool little gadgets, this size, $1,000, and it's easy to use, more or less. Okay, so what's it good for? Well, anything you can use with sequence data. So we can do the usual stuff. It's a bit overhyped. It does low rates. It's a bit overhyped because it doesn't really scale. It seemed like an awesome idea when I started saying, hey, we can just go and do this stuff on the farm, everybody. But right now, it's still not scaling. It will take you 4, 5, 6 hours to get this stuff done. All right, for one animal, it's okay. I have 1,000 animals on the farm. Yeah, that might take a while to get over there. But one that I'm still very sold on is disease testing. This one I think will work fine, because you can do diagnostics on site, on the spot. And that's kind of the one that we are investing a bit more in right now. But anyways, I leave that for you to talk with Hannah tonight. And on that, I'm done, probably way over time already. Yeah, way over time. Any questions?
Cedric, you talk about separate the SNPs to run a genetic evaluation with particular causal mutations or more close to causal mutations.
Yeah.
Did you try that with a multi-trait? Like, how can I assemble that with different traits?
You do this individually, one by one, trait by trait. But computationally, it should be reasonably trivial. You're just looking at 10, 20,000 steps. And you probably can solve effects instead of having to solve it with an animal, because then it's more steps, so you solve effects instead of solving the animal.
Perhaps an idea from Pova and Raven about storing sequence data. Let's say for if you know parents, and then assume that there's not much going on, just record crossover if they're 60. What do you think about that?
Yeah, that was exactly what I was kind of talking about when we said of having this library of haplotypes, because you can match them up to the place where they fit, and you just need to keep this information so you can reconstruct them from that. Yeah, what Paul mentioned is you go through the pedigree, getting the bits of recombination, and then you can set those out, but you can also just do straight matching of the references. and see which bits you want to use to align it. It really becomes extremely small. These files are in KBs for every individual.
But if you just know the point of crossover.
Yeah, the point of crossover, that would work just as well. Or if you just find a couple of times, and then you can stitch them together. Thanks. Is it? Done? Done and dusted? Okay, I'm all of you.